To today's 1W-MINDS seminar. It's my pleasure to introduce today's speaker, Holger Rauhut. Before we get to his vita, let me remind you that you can always ask questions using the Q&A tool via Zoom on the bottom. We will then review the questions. If there's anything that we want to ask that makes sense to ask during the talks, we can interrupt at certain times. If not, then we will ask the questions for you at the end. So yes, our speaker today is Holger Rauhut. He's started his career by studying mathematics at my current institution, the Technical University of Munich, with some study abroad part in Singapore, but also did his PhD at TUM under the supervision of Rupert Lasser. After that, he went for a postdoc in Wrocław in Poland, and then also for a longer time at the Numerical Harmonic Analysis Group at the University of Vienna. I think as a Marie Curie fellow, returned to Germany for a position as a so-called Bonn Junior Fellow, so very attractive junior researcher position at the Hausdorff Center of Mathematics, at the rank of associate professor, building up a group that at the time included myself as a postdoc. But he was there for 5 years, and now for a number of years, since 2013, he's a full professor at the RWTH Aachen University, where he is holding the chair for the mathematics of information processing. I think so. He has won, for example, one of the very competitive and prestigious ERC starting grants for his work. I think that allowed him to make a lot of the contributions that we know him for. But I think what is, I think, one of the very great achievements of Holger is what I think many people are aware of, is this the very comprehensive book about the mathematical introduction to compressive sensing that he authored jointly with Simon Foucault. I think that has been, at least for me, it has been a great help for me and all my students. And I think a lot of people know this book and appreciate it very much. In addition, he is doing a lot for the community. I think I looked it up, and he currently is an editor for 8 journals in our community. So I think that's really great. But of course, then at the same time, he continues to do great work now, moving more into the direction of machine learning, and some of that he will tell us today, talking about convergence of gradients flow for learning deep linear neural networks. So thank you, Holger, for accepting our invitation. We're looking forward to your talk.
Okay, yeah, thank you very much, Felix, for this very kind invitation. So first of all, thank you and all the organizers of this this worldwide seminar. So I think this is really a great initiative, and I enjoy these talks very much. Yeah, so I will talk about machine learning, and particularly on gradient flows for learning deep linear neural networks. Okay, so let's start with the talk. Okay, so well, this is my introductory slide to deep learning. If you cannot see much, that's on purpose, because I thought that nowadays this topic doesn't really need much introduction anymore. I think you all have seen a number of talks telling how great deep learning is and how well it works, and I don't think I have to add much to that. Okay, so yeah, now to the mathematics of deep learning. So deep learning is a great tool for many applications, and it works well or even great in many of these applications. But one of the questions that is well, we're just starting to understand is why actually deep learning is working so well. And yeah, so there are these three questions. Yeah, why does deep learning work? Can we understand deep learning? And also, what can we prove about deep learning? Well, understanding and proving something is related, but maybe not completely the same. And well, there's several mathematical aspects. Well, one could think of more than this, but I will give you a list of certain things that mathematicians started to look at in the area of deep learning and deep neural networks. So there have been contributions to the approximation theory of deep neural networks, understanding which type of functions we can approximate well with deep neural networks and understand the approximation error. Then generalization properties of deep neural networks. If we train them from data, how do they behave for new data? Then stability properties, like, well, we have heard of some of these issues in previous talks, for instance, by Ben Adcock and also last week by Stéphane Mallat. Yeah, it's the keyword adversarial noise, stability under perturbations, and so on. Then also in the previous talk by Mallat, well, this could be summarized under adapting network structure to specific tasks, for instance, inverse problems in imaging and understanding what type of network structures one would need for that in order to accomplish certain things. Graph convolutional networks fall into that. So we heard about this from Gita Kotyniuk, and one can probably list more. What I will concentrate on is the optimization aspect. So often, or mostly, one uses variants of gradient descent or stochastic gradient descent for learning neural networks from data. So we get an optimization problem that we try to solve using gradient descent, and usually you get a non-convex optimization problem. So the question is always, where do we converge to? Do we converge at all? And so these questions. And well, some things have been done already on this, and I will give a very short history, and then study a particular problem in this area. Okay, so well, I guess all of you have seen this, but it's more to set up notation. So we are speaking about deep neural networks. So functions from an input space are dx, and into an output space are dy. Well, often dy is 1, but it can also be multidimensional. And then a deep neural network is simply a composition of single layers. And these single layers are compositions of an affine function parameterized with a matrix Wj and a vector Bj. And sigma is usually a nonlinear activation function that acts component-wise. And the network is called deep if we have, well, several layers here connected. One note here, if one expands the vector x, well, the data vectors in the end with ones, then we can write the vector gj of x and also appended with a 1 as sigma of wj tilde, well, applied to this appended vectors, where we take this matrix here And well, if we change from the matrices Wj to the matrices Wj tilde, we can actually omit the vectors Bj from now on, and we will do so. Well, this will save us a bit of notation. And now let's first discuss the supervised learning setup. So we are given input and output pairs, x1, y1, and so on. And the x's are in dimension dx, and the y's are in dimension dy. And then we would like to find parameters w1 to wn, so these matrices of a neural network parameterized with these matrices such that approximately f of xk equals the labels yk, and well, in practice we even would like to generalize also to unseen data, but we will not focus on that aspect here. And what one usually does, one sets up a loss function. So it's also a bit of art to find the right loss function, but we will keep simple here later on. And in order to well, find such a function, we set up like this functional depending on these matrices, and we add up the losses for all the data points that we get. And then we need to minimize this empirical risk to find a good network. I also would like to discuss a particular case of unsupervised learning. Here one only gets the data x1 to xm and doesn't see labels. And now the task is rather to learn something about the structure of these input data. Or often, I mean, you assume that they are coming from a certain distribution, so you would like to learn something about this distribution. And one way of doing this are so-called autoencoders. So here we have an encoder, G, which maps from dimension dx into d. And you could view g of x as a code for x, and d is usually smaller than dx. So a lower dimensional code, or something like a dimensionality reduction map. And then there is a decoder which goes back from the code to the input space. And then the idea is to try to find neural networks G and H, so the encoder and the decoder, such that if we decode from G of xj, we roughly get back xj. And well, you could say we simply then learn the identity, but the point is that we have really a dimensionality reduction map here, so we cannot learn the identity, because that would mean that, well, I mean, that can only be done if d is at least as large as dx, and so if we do it like this, you can think of that g and h encode some internal structure of the data. And a particular case that is well understood is when G and H are actually linear, then they encode linear subspaces. And these linear subspaces should approximately contain the data. So G projects down to a certain well, low-dimensional subspace, and H goes back into the original subspace, and certainly the subspace is the information you want, because then you know where the data basically lies. Okay, and well, I will not say much about the application, but just that you can do rather cool things with this. So this is an example where artificial images are generated using such an autoencoder, or more precisely a variational autoencoder. So in order to do so, you basically, well, if you let us go back, you just well, you throw away the encoder and just look at the decoder, and as X, you basically throw a random vector, and then you apply the decoder, and then you get back something like this. Well, this is a slight variation of an encoder, but basically you can do things like this, and so these persons do not exist. These images were generated by these autoencoder. Okay. Now, okay, I said we would like to study the optimization aspect, and so we would like to look at empirical risk minimization. And so the task is, again, to find the appropriate parameters, W1 to Wn, of this neural network by minimizing this functional. And this also includes learning of an autoencoder, where we simply say, well, the resulting network is the concatenation of the encoder with the decoder, and then we have matrices W1 to WL for the encoder and WL plus 1 until Wn for the decoder. So this is included as a special case. And well, often, as I already said, one uses gradient descent or some stochastic versions of this. So we start with some initialization. We initialize these matrices somehow, and then basically I'll apply these gradient steps, take the gradient with respect to Wn, and move along this, choose an appropriate step size, and so on. And turns out that this often works very well. And the question now is why? So do we get convergence at least to a local minimizer or to a global minimizer? And so that's the general question here. Well, here's a, I guess, very partial list of results in this direction. So let me just list these results here. So for linear neural networks, so this is the case where the activation function is linear, and we will in the following concentrate on that. You might say, well, considering a linear activation function is probably not so interesting from an approximation viewpoint and generalization viewpoint. This is certainly true, but before trying to solve this problem for nonlinear neural network, we should at least have an understanding for linear neural networks. And so there have been works by Aurora, Cohen, and other people. For instance, they proved a local convergence result that shows that if you start close enough to the global solution, then you get convergence there. Unfortunately, the condition is empty in the case of an autoencoder, where we really have a dimensionality reduction map, and so so we try to overcome this. And then there have been results by Chitur, Liao, and Couillet, where they prove convergence to a critical point of the functional. So we also we also have results like that, but remove some of the conditions there. Then there has been an interesting work, well, for actually nonlinear neural networks by Jacot, Gabriel, and Hongler. And so what they prove is actually convergence to global minimizer if one has random initialization, and they also need to consider the limit of infinitely wide layers. So the hidden layers are, the dimensions go to infinity here. Unfortunately, that was also not very useful if we consider, well, let me go back to the case of an autoencoder, where these inner dimensions are actually smaller than the outer dimensions. So of course, if you let d to infinity, you get the trivial case that we learn the identity. So So still there has to be done something. There's also been interesting work by Chizard and Bach. Here they showed convergence to global minimizers for, again, for wide two-layer networks, and they connected this to convergence in space of measures. There are certainly many more papers appearing here, and but it's hard a bit to follow all this. In any case, the recurring idea is that one looks at the convergence in the function space or even in a measure space, which contain these neural networks. So one looks at them as functions and not as looking at as convergence on the level of the parameter space. For instance, for linear networks, as we will see, that we get an overparameterization, and then there is some non-uniqueness of representing actually the corresponding function. So it may look actually attractive to rather look at this as a convergence on the underlying space in this function space, namely. And this also has the advantage that often one uses at least loss functions that are convex. And so if we just look at this functional as a functional of the function, of the neural network and not of the parameters, then we actually get a convex function. The problem that we will see is that, in these works here, in this limit, we actually consider then actually a vector space of functions, while and the problem that we will see here, we actually reduce to a manifold of neural networks, and then some tools, well, cannot be applied anymore. Yeah, we will come back to that. Okay, so this is concerning the history, or, well, very partial history. And so let's look at now what we did in particular. And so we look at the special case where sigma is the identity and these offsets bj are 0. Well, this is not a dramatic restriction, but of course having sigma being the identity, that's quite much of a restriction, but anyway, so we would like to first understand this linear case before we move on to nonlinear situations. And then f of x is simply the decomposition of all these matrices, wn until w1, and apply all this to a vector x. And now, of course, we can simply write out this multiplication and call this the matrix W. And yeah, a few remarks. So of course, linear networks may not be expressive enough for many applications, but the convergence properties are still non-trivial. The function f of x, well, equal wx is of course linear. And well, the factorization into these single matrices can be viewed as an overparameterization of this matrix W. Now, if we look at the minimum of all these dimensions, then the rank of the resulting matrix can be at most this minimum. And in particular, in the autoencoder case, where one of the inner dimension is smaller than the outer dimension, we really have a restriction on the rank. So R may be smaller than dy and dx, and this actually makes the problem interesting. Okay, then we will simply consider the L2 loss, nothing more fancy. And if we write this out, so put all the data points as columns into a matrix X, and all the labels y1 to ym into a matrix Y, then if we add up all these losses for these data points, then we simply get as the loss function the Frobenius norm of y minus wx. And as a corresponding functional, so this is a function of w of this product, and often we are also interested in the functional as a functional on the single matrices. Then we can write this in this form. And in the autoencoder case, which is a special case, there we simply say the labels equal the data. So there the problem was to actually find a matrix such that x minus wx is small. And okay, this should actually be not x, but w1 to wn. So we get this functional for Ln. Okay, so that's the setup. And it's important to note that this function Ln is not jointly convex in w1 and wn. But as I already said, if we consider it as a function of w, then we really form the neural net, in this case just a matrix, then it is actually convex here. But as we already remarked, the possible w's may have a restriction on the rank, so we are not on a Euclidean space anymore, or not on a vector space, but on a manifold. Okay, and now let's look at the gradient flow. So in order to simplify even more, we move from the gradient descent to a gradient flow. So this has the advantage that we don't need to discuss step sizes. And the problem becomes a little bit simpler. And so the corresponding gradient flow for each of the single matrices looks then like this. We take the gradient of the functional with respect to wj, and that gives the flow for wj. And one can actually compute this gradient for this L2 loss. And this will look like this. And here we have the functional L1 of this product. So this is the matrix W. And yeah, so the question is, does the flow converge to a critical point, a local minimum, or even a global minimum of Ln? Okay, so when we started all this, very early on, we actually had a result for what we call symmetric autoencoders with one hidden layer. And so let me explain this. So we just said n equals 2 and y equals x. So we are in the autoencoder case. And then we have two matrices. And in addition, we say now the second matrix is simply the transpose of the first matrix. So we only have one matrix that we need to learn. And then we have this, call it E of V is the function L2 of V and V transpose, or L1 of V transpose, and we get this function out here. Okay, so we included the 1/2 for convenience, but that's of course not necessary. And now, of course, we have a multiplication here, so V enters quadratically, so we do not get the gradient flow from what we had before, but it looks slightly different. So here, the gradient of V can be expressed in this way. So it's actually a third order differential equation in V, and well, actually, there has been work already done with a very similar differential equation, which is called the Oya flow. And that was done by Helmke, Moore, and Jan, more than 25 years ago already. And so here, what we could get out of this is that, well, we assume that X transpose has full rank. So this will be a common assumption in the following. And well, this is usually satisfied for most sets of data. And we also assume that lambda r, so the r's eigenvalue of X transpose is larger than lambda r plus 1. So we assume that there is an eigenvalue gap at lambda r, which is also not a very severe restriction. And then one can show that for almost all initialization V0, satisfying that V0 transpose V0 is the identity, the flow converges to the global minimum of V. So here we really get global convergence, or convergence to the global minimum for almost all initializations. One can question why not for all initialization. Well, it's possible that, I mean, there are also some critical points which are not the global minimum. And if we start in such a critical point, of course, then we don't move and then we stay there forever. So we need to make a small restriction here. And in the end, we get that for almost all initialization, we have this. And then the question was, well, can we extend this also to the non-symmetric case? And then, of course, can we get this also for larger n? And yeah, unfortunately, the methods that were useful here didn't work in these more general cases. And but let me come to that. Okay, so so as I already said, it's useful to actually look at the product, and so rather than at the single matrices, see what how the product evolves, and then if we form the product, we can actually derive also a differential equation for the product, which looks like this. So it still contains these single matrices, but okay, that's the formula. And let us shortly define this as, well, all these expressions, well, this whole expression as B, depending on W1 to Wn of the gradient of L of W, where W is the product of these single matrices. And let me make a remark. Well, it's a bit for the specialists, but I mentioned this neural tangent kernel. So this is this work by Jacob, Gabriel Hongler. So here, let's say we combine these matrices all into a big parameter vector by sort of flattening out all these matrices. So this gives a vector in Rp, where P is, well, you have this formula for P, and f theta, like it's a parametrized function, is simply this linear function defined with this product. And then in general, the neural tangent kernel, so that's a kernel depending on theta. So for each theta, you get a kernel. And it's defined in this way. So you take derivatives with respect to the case parameter and take a tensor product with itself and sum this up over all parameters. So this is the tool that these people introduced. And then one can associate to a kernel corresponding gradient called a kernel gradient. And then one has actually that this kernel gradient of some function is precisely, in our case, this operator B with respect to these W1, Wn of the gradient of this function. So here we have a relation to this neural tangent kernel business. Okay. And so let me continue now with the actual yeah, the actual business. And so Aurora, Cohen, and Golovich and Hu have showed the following. If the flow has balanced initial condition, which means that we have these relation for these single matrices, and then it turns out that the flow can be written in that way, where now, well, the gradient is, well, we apply a certain operator depending on W to this gradient. And the crucial point is that here we don't get a dependence on the single matrices anymore. So what we get a flow that only depends on the resulting product and not on the parameterization anymore. So this is a useful observation. And if we introduce a map, so this operator depending on W, and we can apply this to a matrix. So here we simply replace the gradient by a matrix, and then in the balance case we can write a differential equation of W just in this form. So we get this equation. They also proved that one cannot write this object here as a gradient of some other functional, but as we will see, we can actually write it as a gradient if we change the notion of gradient. So this will lead to gradient flows on manifolds. And so the manifold we will consider is actually the manifold of matrices W of rank R. And so R is as always the smallest of the dimensions, including the inner dimensions of all the single matrices. And of course the product can then be at most of rank R. And so all these flows, they move on this manifold of rank R matrices. And now we need also the tangent space. So the tangent space are all the matrices of this form. So if so the tangent space of a matrix at a matrix in MR looks like this. And what we showed is actually that if we restrict this operator to the tangent space, then actually we get a self-adjoint and positive definite map. And in particular, this mapping is invertible. Well, you have to be careful. It's only invertible once we restrict to the tangent space. But this is important because then it follows, well, we can form the inverse, and then this object here, which depends on two matrices, and involves the inverse of this operator. This defines a Riemannian metric on MR. And another remark, I mean, well, going back to this neural tangent kernel business. So what people have, the way people use this neural tangent kernel is when they showed convergence result in this infinite bits limit is that also for, well, random initializations, in this limit, they get a kernel which doesn't depend on the parameters anymore, and then they also show that they have positive definiteness, and since they're actually in a vector space, then this actually then ensures already that you have a convergence to a global minimum. But unfortunately, this is not sufficient in this case because we are not moving on a vector space, but on a manifold. And then the fact that we have a convex function doesn't help so much if we restrict it to a manifold. Okay, anyway, so we thought that this is useful observation, and then one can actually introduce a Riemannian gradient using this operator. Yeah, okay. So the Riemannian gradient is defined. So we take this Riemannian metric and then say that we have the Riemannian gradient if for all z's we get this formula where here is the standard gradient. And in essence, the Riemannian gradient is then, well, since here we have the inverse, it's basically, not the negative, but this map applied to the standard gradient. And now if we assume balancedness, and also if initially we are on MR, we recover the flow for the product WT as Riemannian gradient flow on this manifold of rank R matrices. So we get this nicely looking formula. So well, despite the fact that Aurora and Cohen and so on proved that we cannot write this as a standard gradient, we can actually write it as a Riemannian gradient. Okay. Okay, so this was is a nice observation. Although for what we then did in the following, it's not necessarily it's not necessary to have this, but maybe this can be useful in other contexts also. Okay, so now let's look at convergence of the flow. And so here we have the first result is a convergence result to critical points. So we assume X transpose has full rank, and then what we showed is that all these flows, they are defined for all positive T, and this tuple converges to a critical point of this functional Ln as T goes to infinity. So this sets convergence to a critical point. And I should say that this generalizes a previous result by Chitour, Liao, Couillet, where they had the assumption that the input dimension is larger or equal than the output dimension, which is probably fine. But they also required that all the inner dimensions are larger or equal than the output dimensions. And this, of course, immediately excludes the case of an autoencoder. And also one should note that if we look at the manifold of all matrices that we get as a product under this particular assumptions, then we actually get the space of all matrices. So we don't actually restrict to a manifold. Okay, but it's just a remark. Now, how did we prove this? Well, we use a standard result, namely the theorem of Lujashevich, which states that if f is an analytic function and the curve x of t is bounded and a solution of the gradient flow equation, then x of t converges to a critical point of f. This is a very nice result. So we need analyticity, which we have. And so what we need to show is actually boundedness of the flow. And this is what we could achieve in the end. Which in retrospect is turned out to be rather intriguing, because we had difficulty proving this when actually trying to do all this stuff for the gradient descent case and passing from gradient flow to gradient descent. But okay. And now the question is, well, what are the critical points? And since we're in the case of linear networks, and I have a nice, nice square loss, we can actually characterize the critical points. And so we again assume that XX transpose has full rank. We set as Q this matrix involving X and X and Y. And by the way, in the autoencoder case, this is simply the identity. And well, and assume that the SVD of the singular value decomposition of Q looks like this, where Q is the rank of Q. So we don't even assume that Q needs to be a full rank. And then the critical points of L1 restricted to a manifold of rank K matrices are of the following form, where J is a set of indices of cardinality K. And so I choose any of these singular values, sigma j, just k of them. It doesn't need to be the largest one. And if I form this matrix, then it's a critical point. And by the way, if k is larger than q, so if we have here rank k matrices and the matrix Q has smaller rank, then we do not have any critical points when restricting L1 to MK. And for this W, then L1 of W takes the following form, and as a consequence, well, we get a global minimizer. So this W is a global minimizer if and only if the sigma j's that we actually took, these are among the k largest ones. Well, I wrote this complicated formula because it may in principle be that some of the singular values are coinciding. Okay, and I should say that this generalizes a result by Kawaguchi, which required full rank of XY transpose and Q to have distinct singular values. So this is, well, that's maybe a minor point that we generalized it in this way. And there has also been a paper of Trager, Kohn, and Brunner on this issue. Okay, and now, so the question now is remaining. So we have convergence to a critical point now, but the question is this point now a global minimum, or is it actually a saddle point? So by the way, well, all the local minima here in this case are actually already global minima. So the question is, can we avoid local minima? And so the result we have looks as follows. Again, we assume XX transpose to be a full rank, and little q being the rank of Q, and R is, as usual, the minimum of all these dimensions, and R bar, well, if Q is actually less than R, we have to replace R by R bar. And now the statement is that for almost all initial values of these matrices, the single matrices, then the flow converges to a critical point of Ln such that the product is a global minimizer of L1 on the manifold Mk of matrices of rank K. So K is the rank of the limit. And so this would look nice if actually K, we could say that K is automatically R bar because that's the maximal rank that we can achieve. But unfortunately, we cannot say on which of these manifolds we get the global minimizer. So we might get a rank deficient matrix. Okay, but at least for n equals 2, we can exclude this case, and then for almost all initial values, the flow converges to a global minimizer of Ln on this space of matrices. Okay, and in particular, this means that we extended the result for the symmetric autoencoder case to a general case. And of course, the conjecture is that that we can choose k equal r bar in A, and that all, well, in other words, that B extends also for larger n, but unfortunately, the methods that we use don't extend to n larger or equal to 3. Well, in the sense that we cannot say a priori which rank the limit has. Okay, so I would like to shortly go into the proof of this, or at least the proof idea. And these are strict saddle points. So what is a strict saddle point? A critical point of a function f, it can be on a manifold or on a Euclidean space. This is called a strict saddle point if the Hessian has a negative eigenvalue. By the way, we also include maxima here, but in terms of minimization, I guess maxima have the same role as saddle points. And in the case that we have a Riemannian manifold, one has to replace the standard Hessian by the Riemannian Hessian, but I will not go into detail here. And then, so we have the following abstract result. So we let L be a twice continuously differentiable function on a Riemannian manifold, and then the set of initial points, W of 0, such that the corresponding flow converges to a strict saddle point has measure 0. Or in other words, for almost all initialization, we avoid strict saddle points. Okay, so this is the abstract result. So our work here was not so much, because we could rely on, okay, the first comment is we apply this to the functional Ln, but we could also apply it to L1 restricted to the set of rank R matrices. Okay, so as I said, we didn't have to do much work here, because this was essentially proved already before by these people. So they proved it essentially for gradient descent, or like discrete iteration maps. And so yeah, they considered such iterations. And well, they had these conditions on the determinant, on well, determinant of the Jacobian of H, and then similarly, then the set of such x0 such that this sequence here converges to an element here, which can be seen as basically the set of strict saddle points. This has measure 0. And the proof relies on tools from dynamical systems. Interestingly, we could prove the continuous version of this based on this discrete version, which usually you do it the other way around, but in this case, it worked to prove the continuous version by using the discrete one. Okay, and so what remained to do is to characterize the strict saddle points for L1 and for Ln. So we already know what the critical points are, and so we have to say which of them are actually strict saddle points. And so one result in this direction is if we look at saddle points of L1 restricted to MK, then these are always strict saddle points. And if we now look to the parameterization, So we look at the tuple such that the product is this W, which is a saddle point. Then also this tuple is a strict saddle of Ln. So this already means that if you have a saddle point of L1, we basically get saddle points of Ln. Now, so what about the other way around? So let's first consider the case n equals 2, and the rank k here should be less than this maximal rank. And so we assume that we have W, which is the product of W2 and W1, that this should be a global minimizer of L1 restricted to MK, but MK, well, K is not the full rank. And then if we do not have full rank and a global minimizer, then once we go to L2, we actually get a strict saddle point. And unfortunately, this is not true for n larger than 2. So, for instance, if we take the point where we only take the zero matrices, then this is a saddle point of this functional Ln, but it's not a strict saddle point if n is larger than 3. In fact, the Hessian of Ln is exactly 0, so there is no 0 eigenvalue. And this is actually the problem when trying to extend our result to n larger than 2, that we cannot work with strict saddle points, but one has to probably take into account higher derivatives, but the tools are a bit sparse here, it seems. And well, just a remark also, it is possible to have actually a flow converging to 0, even in the case n equals 2. This is of course not a contradiction, because we only said that for almost all starting points we avoid these strict saddles. And yeah, this can be constructed in this way, in the sense that we take an eigenvector of x transpose x and take as starting points for W1 U1 transpose, and for W2 minus U1, and then they both converge to 0. Okay. Okay, so now finally some numerical experiments. So these show some, well, we basically looked at the flow for x minus W transpose x, well, squared, and factorized W into n equals 2, 5, 10, and 20 dimensions. So these are these plots. So and then we also varied the dimensions, and as you can see, we get nice convergence, and these dotted lines indicate the global minimum of these functionals. Okay. And so we verified our theoretical findings, and so here also curves for different n, and it's maybe a bit surprising, but the curves look almost the same for n equals 2, 5, 10, 20, and so on. So here, these are both for the autoencoder case and for balanced initial conditions in the first, for the first two plots, and with non-balanced initial conditions for the other two. Okay, we are currently working also for trying to do the analog thing for gradient descent. This is work in progress, and well, after some initial problems here, so together with my PhD student Maxime Nguyen and Ulrich Tersteege, we are about to establish that under suitable conditions on the step size and also approximately balanced initial conditions, gradient descent, well, also converges to a critical point. And once you have convergence to a critical point, then we also can show that for almost all initializations, we get convergence to a global minimum of L1 on MK. Well, okay, we cannot say precisely that K is always the maximal rank, but at least it's the minimum on MK for some K. And if n equals 2, then we really get the global minimum. Okay, so, but this is work in progress, and yeah, so the details still have to be polished, and we hope that we get soon a preprint out on this. Well, there's of course a lot of open questions. One is of course to prove this conjecture that the global minimum of Ln is the limit for almost all initializations, also for the case that n is larger or equal to 3. And then of course the big thing is to extend all this to nonlinear networks. Of course, here in this work we used a lot of properties from linear algebra, singular value decomposition, and so on, and all this will not be there anymore for the nonlinear case, but we do have some hope to make also progress here. Of course, you can think of many other open questions, but I leave it at that. Okay, so finally, I would like to thank you very much for your attention. And I'm happy to answer questions.
Yes. Thank you very much, Holger, for this very interesting talk. And I again invite everybody who has a question to pose it in the Q&A tool that is on the bottom of your Zoom screen. So we can start with a comment that came in, basically saying that there's a paper from an NYU group which showed an approximate convergence of gradient descent on actual autoencoders with ReLU activation, and that work builds on previous work on ReLU autoencoders. And it would be cool to see if those results can be improved starting from this perspective, I guess, your perspective. So.
Yeah, thanks very much for the hint. Unfortunately, I don't know this work, but I should definitely have a look. And I would be very happy if ideas that came up in our work could be useful there. Yeah, but I cannot say much more.
Okay. So,
So Rebecca Willett has a question, and I think she should be able to unmute herself now and ask it.
Hey, can you hear me?
Yes, I can hear you. Hi.
Hi, Holger. That was an interesting talk. Thank you so much. I was just wondering if you could say a little bit about whether you've got a sense of how these results relate to notions of implicit bias.
Well, I guess we basically studied the convergence here. Well, implicit bias. Okay, so if you think of low rank, like that, one thought is that in these things that one type of implicit bias that a gradient descent can actually give you is low rank. Now, what we do is we basically explicitly put in the rank, because in this factorization, the smallest of these dimensions actually determines the rank, and in particular, if in this autoencoder case, it only makes sense to actually reduce the rank. Now there are other works, and actually my group is presently working also on this, that you actually do not restrict the rank and the factorization, and then look at what happens if you run gradient descent. Like basically you start with an n by n matrix, and then you factorize this into several n by n matrices, and then simply start gradient descent. And it looks like like you first approach low rank matrices, but if you keep iterating, actually the rank increases, and in the limit you don't see this anymore. So it's not really, this bias is probably not really about what happens in the limit, but rather what happens if you stop early. I mean, I guess this is also related to regularization by early stopping. Does that answer the question, or?
Yeah, thank you so much.
Yeah, okay.